Hello guys, welcome to my channel, and in this video I'll explain you article number 2.9 Electrostatics of Conductor. As you know the meaning of electrostatic, electric charges at rest. So whenever we are discussing about electric charges in conductor, we are saying that the charges are at rest, there is no electric current in it. Okay, so this is the thing you have to remember. So now we'll start. Conductor and insulator were described briefly in chapter number 1. Conductors contain mobile charge carriers. In metallic conductor, this charge carriers are electron. Okay, so we have described conductor, insulator. As you know, conductors are the materials in which there are free charge carriers. The charge carrier can move. Okay, but in insulator the charges cannot move. Okay, and in metals, what are these charge carriers? They are electrons. Okay, in metal the outer valence electron part away from their atoms and are free to move. Okay, so what happens in a metal? The atoms, the valence electron, the outermost electron, they are less attracted with the nucleus, with the nuclear force. Okay, or what we not nuclear force, the electrostatic force from the nucleus. Okay, so they get parted, or they get separated from the nucleus by gaining thermal energy. Okay, the thermal energy due to the temperature of the conductor, it will get thermal energy and it will separate out. Okay, so it become free electron. Okay, so now this electrons are free within the metal but not free to leave the metal. Okay, so this electron is free to move inside the metal, but it cannot escape the metal, because as soon as it try to escape, okay, so what will happen? The whole metal will acquire a negative charge, or there are positive charge is acquired by the metal. Okay, so there will be a potential barrier. This electron will again be attracted towards this, so electron cannot escape this potential barrier from the metal. It is free to move inside the metal. Okay, the free electrons form a kind of gas. They collide with each other and with the ions and move randomly in different direction. As you know, the molecules in a gas, there are molecules of gas, they just move in different direction randomly. Similar, we can say electron form a kind of gas. There electrons are moving in different direction at very high speed. Okay, thermal velocity that we call. Now in an external electric field, they drift against the direction of the field. Okay, but when we apply external electric field, so what will happen? In that case, there will be a force experienced by the electron. As you know, the force experience will be minus E. This will be the force experience, and the direction of the force will be opposite to the direction of the electric field. Okay, so they will be drifted against the direction of electric field. This is what you will study in chapter number 3. Okay, so now the positive charge ions made up of the nuclei and the bound electrons remain held in their fixed position. Okay, so the positive ions and the electrons which are not free, they will be bound charges. They will remain fixed in their position. Only the electrons are free to move. In electrolytic conductors, the charge carriers are both positive and negative ions. Okay, so in electrolytic solution, suppose there are NaCl, what will happen? The charge carriers are Na plus Cl. Okay, Cl negative. You have studied this in your chemistry. Okay, but the situation in this case is more involved. The movement of the charge carrier is affected by both the external field as also by the so-called chemical forces. So here are another factor comes electric field also, another factor, that is the chemical forces, that we study in chapter number 3. Okay, the chemical forces, that is the chemical forces or the chemical energy that is stored in the battery. Okay, now we shall restrict our discussion to metallic solid conductors. Let us note important result regarding electrostatic of conductor. Okay, but we will restrict our discussion to only metals, or only metals. Okay, now, so first point we'll discuss about conductors. Electrostatic conductor is, inside a conductor, electrostatic field is 0. This is a very important point. So I'll read the lines for you. Consider a conductor, neutral or charged. There may also be an external electrostatic field. In the static situation, when there is no current inside or on the surface of the conductor, the electric field is 0 everywhere inside the conductor. Okay, so if there is a conductor and there is no electric current, okay, there is no electric current, then the electric field inside this conductor will be, there will be no electric field inside the conductor. Okay, even it is placed in an electric field, Okay, even it is placed in an electric field, even then the electric field inside this will be 0. Okay, this fact can be taken as the defining property of a conductor. Okay, and we can define a conductor like this. Okay, a conductor will be a material in which there is no electric field, whether electric field outside is present or not. Okay, a conductor has free electrons. Okay, as long as electric field is not 0, the free charge carrier would experience force and drift. Okay, so what is the reason of this, why there is no electric field inside the conductor? So in conductor there are free charge carrier, the electrons. In metal there are free electrons. Okay, so they will distribute themselves in such a way that there is no electric field. Otherwise, if there is a electric field, what will happen? They will move and there will be electric current. Okay, but we are saying that we are taking a case of electrostatics. Okay, where there is no electric current. In that case, when charges are at rest, they will distribute themselves in such a way on the metal surface such that there is no electric field. Okay, in the static situation, the free charges have so distributed themselves that the electric field is 0 everywhere inside. Electric field static inside a conductor is 0. Okay, so electric field inside a conductor is always 0. Okay, I'll tell you the example case of the when the external electric field is applied. In that case, what will happen, as we seen in the case of dielectric, similar to that, but here the electrons can move. So all the electron will move this side in the opposite direction of electric field. Okay, and so there is a negative charge here and there is positive charge, and there will be an induced electric field, and this induced electric field is equal and opposite to the external electric field. So the net electric field inside will be 0. This is the case when there is external electric field. In the case when there is no external electric field, then the electron will align themselves in such a way that there is no electric field inside the conductor. Okay, distribute themselves. Okay, I hope this first point is clear to you. Okay, so this is what you have to remember. Electrostatic field is 0 inside a conductor. Okay, so now at the surface of a charged conductor, electrostatic field must be normal to the surface at every point. Okay, so if there is a charged conductor, a conductor has a charge, so what will happen? Suppose this is a charged conductor. I'll draw the conductor like this. Okay, so if it is charged, then electric field must be normal to this this surface of metal. Okay, or I can say the area vector of the electric field should be parallel to the area vector of the conductor. Whether it is parallel or anti-parallel, it can be anti-parallel if the charges are negative. So we'll discuss this now. If we were not normal to the surface, it would have some non-zero component along the surface. Okay, so the explanation is similar to what we explained in equipotential surface. Okay, in equipotential what happens? Okay, so I'll explain it here. Suppose we'll assume that there is the conductor, and if there is electric field and it has a component, like it is making certain angle with this, it is not normal. Okay, so what will happen, we can resolve this electric field into two components. One component will be along the horizontal plane, okay, of this plane of the conductor, and so this horizontal component of electric field, this will exert force on the free electrons. Okay, and there will be electric current, and we are taking the case of electrostatics. There is no electric current, so definitely in the case of electrostatics, when the charges are at rest, even there are charges but they are at rest, there is no current, then the electric field must be normal. Okay, I hope this makes sense to you. So now, free charges on the surface of the conductor would then experience the force and move. In the static situation, therefore, each should have no tangential component. Okay, so this is what I explained you. Thus, electrostatic field at the surface of a conductor must be normal to the surface at every point. For a conductor without any surface charge density, field is 0 even at the surface. Okay, now the third point is the interior of a conductor can have no excess charge in the static situation. Okay, so if there is a conductor and it has charge, then all the charges will reside on the surface of the conductor, and there will be no charge on the interior of the conductor. Okay, a neutral conductor has equal amounts of positive and negative charges in every small volume or surface element. Okay, so if there is a neutral conductor, suppose first we'll take the case of neutral conductor. Then what will happen, in that there are so many atoms, and in a small volume there will be a number of atoms, and an atom is electrically neutral. So a small volume, any small volume of the conductor will have equal amount of positive and negative charge. Now when the conductor is charged, the excess charge can reside only on the surface in the static situation. Okay, so in the static situation, that is the current is not, charges are not flowing, there is no current, then the charges, the extra charges, the excess charges should reside on the surface. This follows from the Gauss's law. Consider any arbitrary volume element V inside the conductor. Okay, so suppose there is a conductor like this, a spherical conductor, and I'll consider a small volume inside this conductor. Okay, very small volume inside the conductor, volume element. On the closed surface as bounding the volume element as electrostatic field is 0. Okay, so I'll take a what this surface, closed surface bounding this volume. Okay, so electrostatic field here is 0. Okay, as we already discussed that inside the conductor there is no electric field. Okay, so there is no electric field. So if I apply Gauss's theorem here, so what I'll say, so what is Gauss's theorem? Applying the Gauss's theorem, flux will be what, or I can say flux is what, electric field times the this area. Okay, suppose the area encloses ds. Okay, and this will equal to what, this will equal to the 1 upon epsilon naught, the charge. Okay, so now we are saying that this electric field is, there is no electric field inside the conductor from the first point. Okay, so this implies that ds cannot be negative. Okay, only thing that can be 0, sorry, not negative, 0 is charge. So this concludes from Gauss's theorem that there is no charge inside the conductor because there is no electric field inside the conductor. Okay, now but the surface as can be made as small as you like. Let the volume V can be made vanishingly small. This means there is no net charge at any point inside the conductor, and any excess charge must reside at the surface. Okay, so all the charges must reside at the surface, and there is no charge inside the surface. Okay, inside the conductor. We'll move to the fourth point. And fourth point is electrostatic potential is constant throughout the volume of the conductor and has the same value on its surface. Okay, so the electrostatic potential is constant all throughout the volume. Okay, I'll explain it to you. This follows from result 1 and 2. Since E is 0 inside the conductor and has no tangential component to the surface, no work is done in moving a small test charge within the conductor and on its surface. Okay, so you see there is no, like this, the conductor. I'll take a plain conductor. This is suppose this is a cuboid. Okay, a conductor, cuboidal conductor. Okay, and in this the electric field be what, it should be normal. Suppose this is a charged conductor, the electric field should be normal, because even it is not charged, it doesn't matter, the electric field is normal, it should be normal, because otherwise, as you will see in the second point, there will be current. Okay, and we are talking about electrostatics. Okay, so now because electric field is perpendicular to the surface, then what is there is no electric field in this direction, and if there is no electric field, so what is the change in potential? There is no change in potential, or I can say the potential difference between any 2 points in this surface is 0. Okay, because there is no electric field. Okay, so there is no potential difference, so no work is done in moving any charge from any points of the conductor. Okay, so hence the result, okay, there is no potential difference between any 2 points inside or on the surface of the conductor. Hence the result, if the conductor is charged. Okay, so you see in the case of uncharged, if the conductor is uncharged, there is no electric field parallel to the, horizontal to the, or parallel to the conductor, so there will be no potential difference, hence there is, the potential is constant. Potential difference is 0, is that means that there is the potential all throughout the conductor is 0. Okay, it's constant, I mean. So now next, hence the result, if the conductor is charged, electric field normal to the surface exists. This means positive potential will be different for the surface and the point just outside the surface. Okay, so this was the case I explained was for charged conductor. If there was uncharged conductor, there will be no electric field, and hence there will be, the potential will all throughout the same. Okay, in a system of conductors of arbitrary size, shape and charge configuration, each conductor is characteristic by a constant value of potential, but this constant may differ from one conductor to other. Okay, so what matters is that any conductor will have same potential or throughout the its inside or outside on the surface, not outside. On the surface the potential will be same. Value of potential will depend on the size of the conductor and the shape of the conductor and the charge configuration, but that it will be same for a given conductor. The potential value will be same inside or on the surface, the value will be same. Okay, so now we'll move to the fifth point, that is electric field at the surface of a charged conductor. So what will be the value of electric field at the surface of a charged conductor? Okay, we have seen that electric field inside the conductor is 0, but on the surface its value will be what? Sigma upon epsilon naught n cap, where sigma is the surface charge density and n cap is the unit vector normal to the surface in the output direction. Okay, sigma, you know, it is the surface charge density, charge per unit area. Okay, how much charge a unit area, small unit area has. Okay, and n cap is the direction normal to the surface. Like here you see there is a surface here, this is the direction of the unit vector. Okay, so now to derive the result, choose a pillbox or short cylinder. A pillbox is something like this, you must have seen. So it is, you can imagine it like a small cylinder. Okay, as the Gaussian surface about any point P on the surface. So remember, from similar to derivation we did in chapter number 1, to find the electric field of a for a continuous charge distribution, what we do, we first draw a Gaussian surface. Okay, and you know what is a Gaussian surface? The Gaussian surface is a closed surface. It has certain properties, like it should pass from the point where we have to find the electric field. Okay, and it should not pass through a discrete charge. Okay, all those properties, it should be closed. Okay, so this is a Gaussian surface we have drawn, a cylindrical Gaussian surface. The pillbox is partly inside and the partly outside the surface of the conductor. So we have to remember that this pillbox is, some part is outside the conductor and some part is inside the conductor. Okay, now it has a small area of cross section del s and negligible height. Okay, this area is very small, but its height is negligible. Okay, negligible height. Otherwise, why we have taken negligible height? If we have taken not negligible height, then what will happen? Then the point will be where we are finding the electric field will be outside the surface. But we are concerned in finding the electric field at the surface. So that's why we have to take the negligible height. Okay, so the point we have to find the electric field is on the surface. Just inside the surface, the electrostatic field is 0. Okay, this is from the first, second, or the previous point we have seen. First point, there is no electric field inside the conductor. So, but you know, there is an electric field on the surface. Okay, so all those electric field must be from where? From the charges on the surface. Okay, thus just outside the field is normal to the surface with magnitude. Thus a contribution to the total flux to the pillbox only from the outside cross section of the pillbox. Okay, so this you have to understand that, you know, there is a electric field normal to the surface we have discussed earlier, and there is no electric field inside. Okay, there is no electric field inside. So the flux, electric field associated with this area should be from the contribution of the charges on the surface. Only these are possible. Inside there is no electric field, there are no charges inside. Okay, so now okay, this equals, the flux is what? Then flux is equal to plus minus E del S. This is the formula of flux. Plus minus, if the minus is for if the charges are negative. Okay, since over the small surface area del S, E may be considered constant, and E and del S are parallel or anti-parallel, the charge enclosed by the pillbox is sigma del S. Okay, so this is the flux, and what is the charge enclosed by this pillbox? This will be equal to sigma times del S. Okay, surface charge density times the small area. Okay, that will be the charge enclosed by the surface, this pillbox or the cylinder. Okay, so we will apply the Gauss's law here, and you know, flux is what? 1 upon epsilon times the charge enclosed. Okay, and when we put this together, and this del S will cancel out, and what we'll get? Electric field is sigma times upon epsilon naught. Okay, including the fact that electric field is normal to the surface, we get the vector relation. Okay, so the electric field will be parallel to the area vector, when it is positive charge opposite or antiparallel to the area vector when it is negative charge. Okay, you get the vector relation from there. This is the value of electric field. But okay, so this is what it is explained, the same thing. Okay, so you have to remember this electric field for at the surface is given by sigma upon epsilon naught n cap. Okay, and now we'll move to the last point, that is electrostatic shielding. This is very important. Okay, so now consider a conductor with a cavity with no charge in the cavity. There is a conductor which it has a cavity inside. Okay, it has a, suppose you can consider like a shell. Okay, shell, a hollow shell. There is no it is a hollow shell. You can say what a hollow shell is. Okay, remarkable result in that case, electric inside the cavity is 0. Okay, so this result must not surprise you, but the electric field inside this cavity is also 0. Okay, whatever be the size, shape of the cavity, and whatever be the charge on the conductor and the external field, and might it in which it might be placed. So it doesn't matter if it is placed in electric field, if it is not placed in electric field, the conductor, or there are charges or no charge on electric field, there is no electric field inside the cavity. This result is from all the point we have discussed till now. Okay, so now we have proved a simple case of the result already. The electric field inside a charged spherical shell is 0. If you go through first chapter, you will see the last proof that we did was spherical shell. Inside the spherical shell, the electric field is 0. The proof of the result for the shell makes use of the spherical symmetry of the shell. Okay, but there we use the spherical symmetry, but the vanishing of the electric field in the cavity of conductor is mentioned above is a very general. Okay, it doesn't matter, the conductor can be of any size. There we prove for a spherical case, a symmetrical case, but for any conductor, any shape of size, if it has a cavity inside, then the electric will be 0 inside that conductor. A related result is that even if the conductor is charged or charge are induced on the neutral conductor by an external field, all charges reside only on the outer surface of the conductor with cavity. Okay, if you can see from here. Okay, if there are charges on this conductor or this charges are induced by external electric field, this charge will reside outside on the surface of the conductor. This is already we have discussed in the previous points. The proofs of the result noted in 2.18 are omitted here, but we note their important implication. We don't have a proof for this. Okay, here we will not do the proof. The NCERT, the proof is not given here for this case, but this result is very important. Electrostatic shielding, whatever be the charge and field configuration outside any cavity in the conductor, remains shielded from outside electric influence. The field inside the cavity is always 0. This is known electrostatic shielding. This is very important. Okay, as I already told you, whatever with the electric field outside or not, if there is an electric field outside, there is a charge on the conductor, but there will be no electric field inside this cavity of the conductor, and it will be shielded from any external electric field. Okay, so this is very important. The effect can be used in protecting sensitive instrument from outside electrical influence. Okay, so this is very helpful. Okay, so what we can do, very sensitive device which can be effective electric field, we can put it inside a conductor with a cavity. Okay, and it will be unaffected by the electric field. Okay, similarly a situation is there when there are chances that there are lightning can strike, okay, at a place. So the best, and this is an open place, so what you can do, and if you're in your car, so the best place to stay protected from the electric field or the lightning is to be inside the car, because the car is made of metal, and it will act as this conductor. Okay, and inside the conductor, the electric field will be 0. Okay, so that is the best safe place to be in case of lightning. Okay, so gives a summary of the important electrostatic property of conductor. In the 2.9, so you see electric field is 0, rho is 0. There is no charge on the surface also. There is no electric field. If there is electric field outside external electric field, there will be charge and induced. Even then there is no electric field inside. Okay, so this is the electric field on the surface, and this is the electric field on the surface. Okay, it is mentioning all the 4 points that discussed, or the 6 points that is discussed. Okay, the potential inside and outside on the surface will be equal. This is the point here discussed. Inside the shell, cavity, the electric field will be 0, surface charge density will be 0. Okay, I try to explain all this 6 point to you. Okay, if you understand it, please give this video a thumbs up, share this video with friends. Okay, help my channel to grow so that I can make more videos in English also. Okay, I have to make videos in Hindi, and I'm trying to make alternatively English Hindi on alternate days. Okay, so I need your support. Please subscribe to the channel, hit the bell icon, and try to share this video as with those who want to read this, want to watch this kind of videos. Okay, and thanks for watching.